Okay, so the next question that we have here is example number 13. And that is example number 13, and that is show that an onto function f is a function from the set 1, 2, 3 to the set 1, 2, and 3 is always 1, 1. Is always 1, 1. Right? So now this is a function that we have basically from this set to this set, meaning that you have 1, 2, and 3. You have this set over here, and you have another set 1, 2, 3, the same set basically. Now, when we are assuming that this is an onto function, so an onto function basically is the kind of function that in which basically all the elements of the codomain every element of the codomain is an image of some element of the domain, right? Meaning that every one of these elements is simply an image. And so basically for example, you can imagine that this is related to this element, and this is related to this element, and this is related to this element, and none of these elements is supposed to be empty. Every one of them is supposed to have been mapped to, because it's an onto function, right? So now that is the assumption that we have made. Now, since that is the assumption, what you need to do is that basically what we are saying, what we want to show is that this function is always 1, 1. Of course, we don't really know any rules about this function. We don't know how these elements are related, but well, we know that it's a function from this set to this set. Now, since we want to show that basically that the function f is 1, 1, so we can prove this by contradiction. Proof by contradiction. Right? So meaning that by contradiction means that let's assume that basically f is not 1, 1. Let's assume that f is not 1, 1. Is not 1, 1. So then there must be two elements there must be at least two elements in the domain of the function there must be and of course 1, 1 means that every distinct element of the domain has a distinct image in the codomain of the function. So if it's not 1, 1, then there must be at least two elements in the domain that have the same image in the codomain, meaning that, for example, something like this, right? So that makes this function not 1, 1. So then there must be at least two elements in the domain that have the same image that have the same image in the range, in the codomain. I'm sorry, in the codomain. Say, for example, 1 and 2. 1 and 2, right? So now what remains here, if basically the image of 1 is, if I make this assumption, then that means that f of 1 is equal to 1 and f of 2 is equal to 1. And so since basically 3, which is the element in the domain, can have only one image in the codomain. Well, and that is based on the definition of a function, then at least then one element of the codomain will not be an image of any elements of the domain, right? Of the domain, meaning that suppose that, for example, the image of 3 is, for example, 2, or suppose that the image of 3 is 3, it doesn't really matter. The image of 3 is equal to 2, then one of these elements is going to be not an image of any elements of the domain, right? And that would be a contradiction. That would be a contradiction. Since we have assumed that f is onto. Therefore the assumption that f is not, here we made the assumption that, let's assume that f is not 1, 1. So then you can say that therefore the assumption that f is not 1, 1 is wrong, and therefore f is 1, 1. So that's basically called proof by contradiction. In many types of situations you can use it in wonderful ways, really. Example number 14. Let's say that you show that a 1, 1 function, f from 1, 2, 3 to basically 1, 2, 3 must be onto. Actually, onto is written this way, right? So you want to show that the 1 function, this function must be onto. So of course, by assuming that, so if this function is basically a 1 function, meaning that you have 1, 2, 3, and under f it is, you can assume that, for example, 1 is the pre-image of 1, 2 is the pre-image of 2, or 3 is the pre-image of 3, or you can do it in any way that you want, but at the end of the day, 1 will be the pre-image of some element here, and 2 will be the pre-image of some other element, and basically, since it's a 1 function, then of course this sort of situation, for example, cannot exist, meaning that you cannot say that you have 1, 2, and 3, right? And 1, 2, and 3, and let's assume that 1 is the pre-image of 1, and then 2 is also the pre-image of 1. That cannot exist because the function is 1, 1. Since the function is 1, 1, then the only way that we can do this is that you can, if 1 has been mapped to from the domain, then no other element can be mapped to that element anymore. And then 2 has to map to, for example, either 2 or 3. So let's suppose that 2 is mapped to 2 and 3 is mapped to 3 under f, something like this. And since there are 3 elements in the domain, 3 elements in the range, there is no way that the function cannot be onto. And let's see if my logic was okay for this situation. The solution is, since f is 1, 1, 3 elements of 1, 2, 3 must be taken to 3 different elements of the codomain 1, 2, 3 under f. Hence, f has to be onto. The same logic, basically. And as a remark, you can say that the results mentioned in example 13 and 14 are also true for an arbitrary finite set x, that is a 1, 1 function f from x to x is necessarily onto, and an onto map f from x to x is necessarily 1, 1 for every finite set x. In contrast to this, example number 8 and example number 10 show that an infinite set, this may not be true. In fact, this is the characteristic difference between a finite and an infinite set. So this is an important remark here, which needs to be noted. So as a remark, we can say that the results mentioned in example 13 and 14. So we had example number 13 and 14. In 13, we said that basically, we had 2 finite sets. Basically, if I take this as set x and take this as set x, 2 finite sets x, and if provided that f is onto, then basically f is always 1, 1, right? If it is onto, then it is always 1, 1. And also, if basically the sets are, if you have 2 finite sets x and x, if f is 1, 1, it must be onto as well. There is no other way. So these are true for an arbitrary finite set x. So these 13 and 14 are true for These are true for an arbitrary finite set. Arbitrary finite set X. That is a 1-1 function f from x to x, a 1-1 function f from x to x, which is basically this case over here, is necessarily onto and an onto map f from x to x, and an onto map basically f from x to x is necessarily 1-1. And of course, in both of these cases, it's necessary that we are talking about the same basically sets x and x, and it's necessary that x is a finite set. If it's an infinite set, then basically these two rules are not necessarily true. Okay. Now, in contrast to this, example number 8 and 10, example number 8 and example number 10 show that for an infinite set, for an infinite set, this may not be true. This may not be true. Meaning that it could be true, but it may not be true. In fact, this is a characteristic difference. This is a characteristic difference between a finite and an infinite set. Between a finite and an infinite set. Infinite sets. So that was basically all about examples number 13 and 14. In the next video, we will talk about exercise 1.2. We have about 12 exercises there. We will go through those exercises as well. So I'll see you in the next video, and thank you.